Today we'll discuss another important problem of finite quantum well. In this problem, we have finite potential barrier. Now it is V0. Previously, we solved the particle in a box problem where certain layer, which is called as quantum well in application, is surrounded by barriers where the potential was infinity. That problem is also one of the most important problems in quantum mechanics. Here, instead of infinite potential barrier, we now have finite barrier height. This is the realistic problem of semiconductor devices. So, realistic potential, often seen in semiconductor heterostructures. Heterostructures mean structure with different band gaps. For example, formed by having a material like gallium arsenide, whose band gap is on the order of 1.5 electron volt, sandwiched between two layers of a material with a wider band gap like aluminum arsenide, whose band gap is on the order of 2.5 electron volt. They are grown by molecular beam epitaxy or chemical vapor deposition with control of the layer thickness down to monolayers. So we can control the thickness of semiconductor materials in the unit of monolayer, single atomic layer. So in semiconductor growth technique, we usually use something called substrate first. Substrate. In Korean, it is called as 기판. This is like a bottom plate to do anything. And then we start growing. It means we grow atoms. Okay. For example, we can grow gallium arsenide, gallium and then arsenide, gallium, then arsenide, gallium, then arsenide. We can grow single atomic layer, and then we grow additional layer like this. Okay, one layer by another layer. So let's say we have gallium arsenide like this, and then if we want, we can grow aluminum arsenide, aluminum arsenide, aluminum arsenide like this. So one layer by another layer, and then we have heterostructures. Here, let's say we have aluminum arsenide, and then gallium arsenide, different material. They are atomically bonded with each other. Then it is heterostructure. In semiconductor devices, the most important concept is the band gap. Okay, so that's the way we assign the band gap of each material. And those are actually the basic idea of many semiconductor devices, such as HAMT, high electron mobility transistor, LED light emitting diode, LD laser diode, and various photodetectors. The basic idea to understand the operation principle of these devices is actually finite quantum well. And here the finite quantum well has this basic structure. Okay. There is quantum well from minus A to A and barriers in region 1, in region 3. Their potential height is V0 now. So previously it was infinity. If the potential is infinity, wave function was set to be 0. Wave function was set to be 0. So we only calculated wave function in region 2 previously. But now it is a little bit more complicated because it is finite now. So the wave function cannot be 0 anymore. Okay, so we need to calculate wave function in region 3 too, and region 1, and then at the interface here or boundary, the wave functions should be continuous. So these are solved based on Schroedinger equation. This is the time independent Schroedinger equation. Now the potential part V is either 0 within quantum well, absolute value of X is smaller than A, or V0 for barrier where absolute value of X is larger than A. So basically when X is A or minus A, that is called as boundary. In applications, we call it interface. Okay. So we start solving the equation from region 2 inside the box or inside quantum well. Inside quantum well. For the region inside the box, potential is 0, and Schroedinger equation reduces to this one. So equation is rather simple. We solve the equation like this: psi 2 double prime is equal to minus h bar square, there should be 2m psi 2, right? Then this one is replaced by k square, so that k is defined as square root 2me divided by h bar, so that the equation becomes this one. This is a well-studied differential equation, an eigenvalue problem with a general solution of, just like we did before, of psi 2. You take the second derivative and you have the original mathematical form multiplied by minus k squared. That's when we have either sine or cosine functions. So most general solution will be a sine kx plus b cosine kx. And the energy E is defined by h bar square k square over 2m. Here a and b can be any complex numbers, k can be any real number. So outside the box, for the region outside the box, like region 1 and region 3. Since potential of V was V0, Schroedinger equation becomes minus h bar square over 2m d square of psi 1 dx squared is equal to E minus V0 psi 1. Now we have this part. Two possible families of solutions depending on whether energy is smaller than V0, the particle is bound in the potential, or 2, energy is larger than V0, the particle is free. So in this potential structure, V0 and potential is 0, V0, let's say we have certain energy levels, we will calculate the lowest energy state E1 until will be like E2. Let's say there might be some energy E. Calculate from this Schroedinger equation where energy E is larger than V0. Then electron in this energy state will just have pass through, because it will have this amount of kinetic energy, so it will just pass through. In applications, actually we cannot use these electrons because the speed of electron is extremely fast. So when you operate your actual devices, this electron will be already gone, and you only have electron in E2, electron in E1, okay, in operation time scale. So this one, which is free particle case or unbound case, sometimes we call it unbound, and this is B, bound, unbound. It's not interesting. So for a free particle energy larger than V0 and letting kappa, now instead of K, kappa you could introduce, then like this way, can square root to 2m E minus V0. Please note the energy is larger than V0, so that this is positive, so that we take the square root, so this is the real number, then it produces this equation. So for example in region 1, okay, with the same solution form as the inside well case, you take the second derivative and you induce minus kappa square, so you will have these equations as a solution to this Schroedinger equation. We will ignore this part of unbound state. Okay. We rather focus on the bound state when energy is smaller than V0. Okay. Energy is smaller than V0. Okay. Then, okay. D square psi 1 dx square is equal to minus h bar square 2m e minus v0 psi 1. Yeah, then you can see that energy is smaller than V0, so this is negative. There's another minus sign. We multiply them, you will have positive number. So we set this as alpha square. Okay. In this way, alpha square is defined to be the same with this one. So this is the way we defined alpha equal to square root 2m v0 minus e over h bar. And we have Schroedinger equation as shown here. So we take the second derivative to induce alpha square. Okay. Multiply by original equation. So this is actually the case of exponential function. So solution will be either e to the minus alpha x, e to the alpha x, where the most general solution is now their linear combination with certain constant multiplied to them. Likewise, for the other region outside the box, region 3, you can calculate exactly the same. It will be exactly the same equation because we have the same potential V0. In region 3, actually, it is just like this, psi 3 double prime equal to alpha square psi 3. Okay. Then the solution will be either e to the minus alpha x, e to the alpha x, and then most general solution should be multiplied by certain constant. Okay. So this is not new, actually this is the basic strategy of differential equation. Okay. Probably you are supposed to study it, such differential equations from like second year of undergraduate courses. Now in order to find the specific solution for the problem at hand, we must specify the appropriate boundary conditions and find the values for A, B, F, G, H, and I, or there are too many. So basic idea is, look at this. Now we need to know F, G, H, and I, and actually in region 2 there was also the Schroedinger equation where we have like a sine kx plus b cosine kx, right? Remove the other part. So we need to determine these values. Okay. Here we will consider several conditions as listed here: boundary conditions, parity, and the finite wave function. This is all because we have many constants to determine: f, g, a, b, h, I. There are too many. So we will use some intuition to make it simple. Yeah, we are familiar with boundary conditions now. Solutions to the Schroedinger equation must be continuous and continuously differentiable. This means that not only the wave function of psi, but also psi prime should be continuous, because we know that the wave function is determined from Schroedinger equation, which is actually second order differential equation. So second derivative is related with original wave function, most of cases multiplied by something else. For example, so second derivative is actually finite, then the first derivative, psi prime, should be continuous. That's the mathematical condition. And the second condition here is there should be definite parity. Parity here we mean that wave function psi should be either even or odd. Okay. This is applicable because the potential shape is symmetric. Okay. In any mathematical problem applicable to nature, when potential is symmetric, the solution should be either even or odd parity solution. So we know that in region 2, wave function was a sine kx plus b cosine kx. We know that sine function is odd function, cosine function is even function. So it means that as long as potential is symmetric, wave function psi 2 should be either sine only or cosine only. Okay. Also, wave function should be finite. we see that especially in region 1, if x becomes minus infinity, then this goes plus infinity, then exponential function should diverge. It goes infinity. But wave function psi should be finite, right? Finite. It means that f should be 0. Likewise, in region 3, because x can go to infinity, this part goes infinity. It means I should be 0. Okay, I should be 0. And another point here is, let me remove this. Another point here is, we see that this one 0, we ignore this, we see this 0, then we have this g e to the alpha x and h by e to the minus alpha x. Here g and h should be the same because the wave function should be either even or odd, okay, in parity. There could be sine or cosine function in the middle, and then there comes exponential function. So let's say there might be certain cosine function in the middle for energy E1, and then wave function should be continuous from this point. Okay, so and there's exponential decay, so it should be decreasing like this, decreasing like this. So in this case, we are considering the even parity solution. Even parity. So g and h should be the same. If it is odd function, actually like a sine function, for example, then sine function, could be there, okay, somehow, right, like this. Yeah, then again we might need to consider g versus h. Then for the case of sine function, actually g and h should have opposite sign. So g and h should have the same value, or we just multiply by -1, but the sign itself doesn't matter here, because eventually what we are interested in is the probability to find a particle at a certain position, that is the absolute value. Then we take the square. So even though g and h, whether they have the same sign or opposite sign, it doesn't matter, because we're gonna have this process eventually. So we'll just choose g equal to be h to make it simple. So for region 2, odd parity solution, psi 2 should be a sine kx. Even parity of psi 2 equal to b cosine kx. And we will start from even parity solution first. Actually, in nature, you will see that even parity solution will always have lower energy. nature somehow prefer the even parity to have lower energy. Lower energy state is most important state in applications actually, because electrons always prefer to go down to lower energy state. Okay, so we made the wave function to be simple like this. Psi 2 b cosine kx even parity solution, psi 1 g alpha g e to the alpha x. Then we apply boundary condition at x equal minus a. So psi at x equal minus a, then we put it minus a here, then b cosine ka, put it minus a here, then g e to the minus alpha a, right? And the first derivative should be also continuous, this one. So we take the derivative of cosine function, right? Then we know that it will be minus b k sine kx, right? Then we put minus a, we put minus a here, then minus sign goes out, it becomes plus, and x is replaced by a, right? So we have this one, bk sine ka. Right hand side, we put minus a here, so then take the derivative, so we have alpha, so alpha g, then e to the minus alpha a, right? So we have these two equations. There's cosine and sine. So we can easily see that we divide 2.2, this one, by 2.1, right? Then we have tangent Ka multiplied by K, right? Then we divide this one by this one, so we have alpha. Alpha was previously defined as shown here, and K was defined as shown here. So alpha square and K square, we sum them up. Alpha square and K square, then alpha square and K square, it is h bar square. We take square, then 2m v0 minus e plus h bar square 2m e, then minus e plus e, they subtract each other. We only have this one, 2m v0 over h bar square. Okay, and then we multiply a on both sides, because we have Ka within this exponent, so we use Ka here and another a here. So we have alpha a equal to Ka multiplied by tangent Ka. This alpha a is now replaced like this, because from this equation we can see that alpha square a square is equal to h bar square 2m v0 a0 a square, I'm sorry, a square minus k square a square. So we take the square root, then we have this one, right? Alpha is replaced by this square root function. Now we see that this is like a tangent function. So if we have like tangent, if Ka is set to be like t or x, some independent variable, let's say it is like tangent x, and we know the structure of tangent x as shown here, then it is multiplied by x. Here this one, this is all fixed value, there's no independent variable, there's a variable here, right? So it's like there is certain fixed variable, we set it like r square, and this one minus x square. Yeah, so two different functions should be overlapped to have a solution in terms of x. And we know the tangent x function, and we multiply it by x. Okay, so the slope becomes steeper like this, but it goes infinity at pi over 2. The same here, slope goes steep, it goes infinity as 3 pi over 2. And same here, we just multiply by positive x value, then it goes like this, still it goes minus infinity, right? And this one is actually, let's consider certain function like this. This is, let's set this y is equal to x tangent x, y is equal to r square minus x square. Here x is actually Ka, and Ka is set to be positive, and this one square root, so it should be positive. So x is positive, y is positive, so we only care this part. X is positive, y is positive, and this one is actually a circle. If we take the square, then you will see that r square minus x square, right? So this one goes here. So x square plus y square is equal to r square. That is a circle with a radius r. Okay. Alright. That will be discussed more in detail. Now we draw separate curves for y equal to Ka tangent Ka, y equal to r square, square root to r square minus Ka square, where r square is set to be 2m v0 a square h bar square. So r is certain value depending on the quantum scale, barrier height, mass of the particle, Planck constant. So the intersections of two curves in equation 4 gives the solutions as exemplified in the right hand side. Exemplified Wide. Okay. For example, if R is 8, then this black solid line is y equal to Ka tangent Ka. And let's say this Ka is W. W is the independent variable, so x-axis now is indicated by W. This is y. And this curve is compared with this circle with radius r equal to 8, right? And this function goes infinity at pi over 2, and it starts from 0 and goes to infinity at the point of 3 pi over 2. It goes infinity here again. It's like 5 pi over 2. And this one is like 2.5 multiply with pi like this. Right, so this is like a 7 point something like that. Okay, I guess 7.8. So it is here. Okay, so it goes infinity around this one, 5 pi over 2, and radius is slightly larger. So we draw two curves, then we see that there are 3 intersection points. Okay, the values of W can be calculated numerically in this way. Actually, this equation cannot be solved analytically. It can be only solved numerically. It means you need to use MATLAB or Mathematica. But intuitively, we can draw these curves. We see that, oh, this intersection point should be the solution. So we have 3 different points. It means we have 3 different energy states. Okay? Because at each point we can fix K value, and K value represent the energy. So we see that there are 3 different energy states. Okay? Anyway, numerically we actually can calculate like this way: W equal to 1.395, 4.165, 6.831. For example, this one is now the W, Ka. Okay, so depending on the A value, we can calculate K. Okay, K is a function of energy, right? So K was defined as h bar square root 2me. Right. So if A is given, and from this value we can calculate energy E. That's the way you can calculate E1. Okay. So energy E was given here, so we multiply A square here, then we need to multiply A square in the denominator, then Ka square becomes W square. We put this number into here, then we can calculate this. Like h bar, we know h bar is like 6 point something multiplied by 10 to the minus 16 electron volt sec, and mass, let's say it is gallium arsenide mass, then it's like a 0.0067. Free electron mass should be multiplied. Free electron mass is like 10 to the 5 by 5. Oh, 10 to the 6, I'm sorry. 10 to the 6 by 5 electron volt. And A could be like several nanometers. Yeah, A was the half of the quantum width. Yeah, let's say quantum width is the 2 nanometer, then A should be 1 nanometer, 1 nanometer. Then you can calculate E1. Okay. This is the conventional method actually. This is the way we can calculate the lowest energy state in finite quantum L in realistic devices. Simple but useful. It might look complicated at first glance, but you will get familiar with this if we pursue the semiconductor studies in the future. So this is actually a very good example to calculate the lowest energy state E1. Anyway, there exists at least one solution always. Please note that we change this R value. It goes smaller. It means potential height is smaller and smaller because of this equation. Look at this. R is related with V0. V0 is getting smaller, R is getting smaller. So R is getting smaller, but still at least one intersection is there. That one intersection goes to even solution. If R is smaller than pi, this one, pi is here, then one solution, right? One confined state exists. So if we extend this, generalize this, then if n pi, R is larger than n pi, smaller than n plus 1 pi, then there are n plus 1 confined states. Once K and alpha are decided, B and G can be decided based on the normalization condition. But we will focus on calculating energy value for now. Okay, so even parity solution. Final note here is consider the case when V0 is very small. Then Ka should be small. Then binding energy, which is the difference between the potential barrier V0 and calculated energy value. And this separation is actually binding energy. Sometimes we will use delta. Then V0 minus E can be like this. Yeah, it can be simplified like this way. This is a little bit getting beyond our class, but sometimes we make very shallow quantum L. Shallow quantum L means this V0 is very small, like this one. Then the binding energy can be given like this way, simplified, and it's a simple function of V0. From the shape of wave function, psi 3 was g e to the minus alpha x. Alpha is given here. It's also very small, okay, because V0 minus e, they are very similar. They are similar with each other. This implies that wave function penetrate a long way, because wave function shape is like this. Alpha is very small. Alpha is very small, then exponential function decays slowly, right? Right? Yeah. So it means wave function shape is slowly changing along this. So wave function penetrates a long way into barrier, then probability of finding the particle inside the well, inside the well, we should say, inside the quantum well, is small because wave function is penetrating. It's leaking a lot when the barrier is low. Well, the detailed procedure for calculating the binding L, this one is shown here actually. It can be found in some quantum mechanics classes, but we'll skip this because, I mean, if you want, you can go through yourself. It's not that difficult actually. We just go through the Taylor expansion of tangent function as shown here and go through some simplification processes. Yeah, but this concept is actually very useful in semiconductor application. That's why I'm introducing this part. Okay, odd parity solution we will now consider. Let's consider the odd parity solution. Then psi 2 in quantum L should be sine function a sine kx, and wave function in region 3, psi 3 is equal to g e minus alpha x. Okay. Then we apply boundary conditions. So wave function should be continuous at boundary. So x equal a, we put it there. So a sine k equal to g e to the minus alpha a, and also psi prime is continuous ak. So we take the derivative here. So ak cosine k x, that x is replaced by a. So ak cosine ka equal to minus alpha g e minus alpha a, right? Yeah. Then divide 2.2 by 2.1. This goes to denominator. This goes to numerator. So we have k cotangent ka, and right hand side these two minus alpha. Then multiply both sides by a, then minus alpha a is equal to ka cotangent ka. Here we know that alpha is equal to square root of 2m v0 minus e over h bar. K was defined square root of 2me h bar. So previously we introduced this alpha square plus k square equal to 2m v0 h bar square. So we have ka here, so we'll apply a square, a square, a square, right? Then alpha a is equal to 2m v0 h k square h bar square minus k a square. So we take minus 1 on both sides, then it goes this one and this one, right? So this is same with minus ka cotangent ka. Yeah, just like we did before, ka is set to be w, an independent variable. Yes, and this one goes like this, r square minus w square. Then we see that again there's a circle, there's a function, yeah, on the basis of cotangent x or cotangent w. This is the shape of cotangent x. It is 0 at the point of pi over 2. It goes infinity here, right? It goes minus infinity here. At pi, it goes infinity here. 2 pi goes minus infinity here. And then we multiply it by minus w. If it is minus w, then we will consider this one like let's say this is w. Then we consider cotangent w. We multiply it by w. Then wave function, no, not wave function here, I'm sorry. W cotangent w will be minus w. It will be like this way. It's changing rapidly, like this, right? It will be changing rapidly. Like this. Yeah, this dotted line will be minus w cotangent w. So again we have two curves. One is minus w cotangent w, the other is a circle as shown here, square root r square minus w square, indicated by red line. Then we have intersections. For example, at r equal to 8, we have 3 intersections. The values of w's and the energy. W is fixed and energy is fixed. Can be calculated numerically, although the graphical method as shown here is great for seeing the solution. I mean, intuitively it is good. It is not an accurate method for getting the numbers. So again, mathematical or MATLAB will give you the exact numbers. For r equal to 8, 3 values of w's are given here. This implies there are 3 odd parity solutions with 3 different energy states. Note the highest level is nearly at the top of the barrier. The values of W can be converted to energy as we did before. Okay, so here we see that there exists no odd parity solution when R is smaller than pi over 2. Look at this. At this point, pi over 2, this function goes 0. Okay, if R is smaller than this one, there is no intersection, so there is no energy state. So sometimes when R is small, it means V0 is small, then there is no odd parity solution. But previously, even parity solution always exists, right? That's the difference. If r is larger than pi over 2, smaller than 3 pi over 2, what does it mean? It is like this, okay? Right? This is r, okay? So pi is here, this is 3 pi over 2, the 0 point, and r is located here. In this case, only one confined state exists. Because there is only one intersection point. Likewise, you can generalize this one. If n minus 1 over 2 pi smaller than r is smaller than n plus 1/2 pi multiplied by pi, then n confined states exist. If r goes to infinity, the intersection points are at ka equal to w equal to n multiplied by pi over 2. R goes to infinity. What does it mean? R goes to infinity. It goes very large. So it goes to infinity. Then intersection should be here, right? Right. So W should be pi, and then it goes infinity. So it should be intersecting here. So 2 pi, where this function goes infinity. Okay. And so. Intersection point at here, this is the case of infinite barrier. Actually, this is more generalized case, because now we are seeing total solutions. So not only the circle, but also the even parity case with the W tangent W, which is indicate by blue lines, and also this one minus W cotangent W. So we also consider even and odd parity cases at the same time. Then those intersections are all correspond to energy state. And here again, if R goes infinity, then you will have solutions here, here, here. So this is case of pi over 2, here pi, so 3 pi over 2, 2 pi, and so on. Okay, it is repeated if R goes to infinity. So if we consider both even and odd cases, then you will see that eventually W is equal to n pi over 2. Okay. All the available states are given by considering both odd and even parity solutions, as summarized here in this figure. Okay. So for R equal to 8, there are 1, 2, 3, 4, 5, 6 energy states. So let me summarize the wave function and probability of both even and odd parity solutions. So here we start from even parity for the lowest energy state, where the quantum number n equal 1. So the energy is defined by E1. Then this is the wave function in region 2. The shaded region is the quantum well, okay, where you see the cosine function, and then sine function, and then cosine function, and then sine function. And outside the quantum well, we have exponentially decaying function here, represented by g e to the minus alpha x. And when we take the square of the absolute value, then we have probability. We see that we take the square, then wave function square is like this, yeah, square. Then we have many more nodes as we go up with larger energy. So the amplitude of this probability is changing rapidly in space. So in wave picture, you can consider that the wavelength of this energy state is smaller than this one, okay? And as we go down and down, wavelength becomes larger and larger, okay? Alright, that's it for today.